Any questions before we debrief the foreign class assignments?
If we would put I assume that if we put the function pointers in different positions in this circle and triangle relative to the start of the structure, it won't work.
Yeah, it's a good thing to consider is the location of those pointers, and why don't I just dive right in because that's one of the topics. All right. Let's see, let me do this a little bit differently. So let me bring up, let's see. Okay, so if I look at this code, here's our triangle and circle. We've got color. I wonder if I can make that blue. And if I had something that is more computer-like. No? Bold. There we go, that looks good. We've got, for the triangle, we have color. We've got this VTTRI, and if I hunt for that, that's got two function pointers to draw an area. So I'll say draw pointer, area pointer. Then our triangle has a character for the shade, base, and height. Okay, I'll put that right there. And I'll repeat the process. And it's really quite similar for circle, except for we have radius here. So let me get rid of base and height and put radius here. Okay. So what I'm trying to give a sense of is how this kind of a pictorial representation of how this would look in memory. And I've made this, I've specifically made a conscious effort to make these rectangles different sizes just to indicate that they're really, let's just say for the sake of argument, radius is some really large variable and it just takes up more memory than base and height combined here on the triangle side. So this is our triangle. This is our circle. And then, I can go ahead and do this. The alternative method of me visualizing this could be with like the traditional ribbon of memory view, but I'll go with this box view. And these things get initialized. So this draw pointer here ends up, let me start down here. This points to some code. And this points to some code. Likewise. So this is, that's horrible, even for me. There we go. So we're all comfortable with this, right? That this is the way this kind of laid out in memory, and we'll drill down on it a little bit. This would be, if I look then at memory as being sequential, and in this case marching down from this pictorial representation, this beginning here would have some sort of offset of 0. This would have, let me use a different color. So have an offset of 0. Maybe I actually ought to put it outside it to kind of emphasize it. So this has an offset of 0. And I'm just going to do kindergarten offsets here. I'm just going to add 1 to the offset for the next member. But what that, in a very real sense, represents is how many bytes from this location, right? So I have to go 5 bytes in my simplified version to get the height. Yeah? 0, 1, 2, 3, 4. Okay. So that's how this is set up. Now let's go straight to do poly. We will focus in on this function here, sp.tri pointer. I'm going to shrink that. Just put it. So by me putting the .tri pointer, I'm not changing anything with regards to memory, meaning that shape pointer SP, let's look at it, it's a union, right? So there's only one pointer occupying memory here. So I'll just say that that's this one pointer sitting right here. And when that pointer is called on a triangle, it's pointing to this object right here. The address inside that pointer is the 0 index, if you will, of that chunk of memory right there. So it's going to, now we have the arrow here, and vttri.draw, that's this right here. So it's going to go to that pointer, and it's going to execute this code right here. And then there's something a little funky that happens, is that we are passing in sp.tri pointer, right? This thing on the left is also the argument to the code. So what we have in the code here, let me put it in red, is we have a pointer here, and what is that address? Where is that pointer pointing, if I'm going to do it in colloquial terms? Yes?
As the triangle at the zero field part of the structure.
So when that code executes, that's what it's getting. Now, what does it do? Well, this is going to do draw, and it does it for both of them. I'll just show it on the one. It's going to do either the draw or the area functions, so I can hunt that down. I guess it's not really that critical. Where's my area triangle? So it executes this code. It's been given this, and what it does is it takes the base times the height, divides by 2. So it takes that, and divides by 2. Well, that's how it works with triangle, and all that actually is consistent with how this is written. I wrote this for triangles, but then down here in main, I didn't only do that, but what I did is I also passed in one of these circles, right? So here's my loop. I'm calling do poly. A couple of these, it looks like the second and last item here, are circles, not triangles. So what happens is we call the do poly function, and this time we pass in this, right, this address, this pointer. It thinks it's a triangle pointer as far as how it compiled, right? We kind of fooled it. But indeed, it's a circle coming in, and we say we want to call the draw function. So there's some code here, or the area function. I guess I'm doing area as my example. And that address is coming into that code. Now it's going to execute that code. And what is that code? That's this. Do the radius squared, right? So it goes down here, it grabs the radius, squares it, gets the result. So even though the reason this works is that ultimately, what the do poly function is doing is it's just taking offsets. It's saying when I say arrow VTRI draw, the second step is to execute the code. The first step is to say where is that code, and where is the second step is to execute the code at an address. The first step is to get that address. And when you do this right here, what's being compiled is that what you need to do is go to offset 1, grab that address and execute. Go to offset 1, grab that address and execute. Or go to offset 2 and grab that address and execute. Go to offset 2, right? And note that it doesn't matter whether it's a triangle or a circle at that point. As long as it goes to the right offset and executes, it blindly will either execute this code or this code. Yes?
Repeat steps 1 and 2. What are the steps 1 and steps 2?
Step 1 would be to obtain the address at an offset. The second step would be to execute the code at that specified address. And I can put a million types in there as long as at offsets 1 and 2 there are these draw and area functions. Now what the draw and area functions do, who knows? You could have it print out to a printer or interrogate a weather station, right? The sky's the limit as far as what the functions do, as long as at offset either 1 or 2 there's an address to that function. So the code doesn't know at all what type it's working with. It's blindly going to offsets and executing code. Or in the case of, or it's going to offsets and grabbing attributes. But how did this thing get set up such that this pointer is pointing to triangles draw code and this pointer is pointing to triangles area code? If we don't know, if that do poly function doesn't know what this is, how did these get initialized in the first place? Where does that happen in our code? Yeah?
Inside the set.
Yeah. There's exactly one point in the application where you're 100% guaranteed to know what kind of thing it is. And that's when you create it, initialize it. I'm combining, they're two separate things, but I'm mashing them together. So when I initialize my triangle, here's where I'm setting up those function pointers. Because I know it's a triangle at that point, I can go ahead and set those pointers up right then. And this is what happens with the library project. Our search results don't have the slightest idea of whether we're dealing books, periodicals, films, or videos. But there is one place where you do know what those are, and that's where you have your news statement and you're creating your book or your video or whatever. And what you're not seeing that's happening under the hood with that constructor is it's setting up those pointers to books display function or videos display function when you're creating a video. So let's look at a bit more detail at, well, then what exactly is a class object? Display function, we will do cout first equals first. And the constructor, I'll start out using an initialization list. First, second, third are my private data members. Now what do we initialize them with? FST. Got to create a main function here. MC.display, oops, semicolon. All right, everyone comfortable with that? 3-integer function, initialize it with the constructor, be able to display it. Let's do a quick sanity check to change the prompt here. Yeah, go ahead.
Braces are after the constructor initialization.
Yeah, line 15 is the initialization list.
Braces.
Huh?
Curly braces.
Am I missing something? All right, there you go. G++, standard equals C++11. This is called myclass.cpp. We can run it. All right, everything's as expected. Now, let me create a long integer pointer. I'll call it IP. What I'm going to do is I'm going to set IP equal to the address of MC, our class object. Which seems weird, taking an integer pointer and assigning the address of a class. And if I try to compile it, it's actually going to vomit because it's saying, no, you're not allowed to do that. Yeah, the types aren't compatible. So what I can do is use a sledgehammer cast. So this is kind of the C++ way of doing it. If we're doing it the C way, we would have just done something like that, right? That's the C version of it. Same thing. Yes?
Is reinterpret cast only for pointers?
No.
Difference between static cast and reinterpret cast?
Static cast has some consideration for object inheritance. Okay, so what am I doing here? Cout. Let me come back up here. I just find numbers 25 through 14. Now we can see all that on the screen at the same time. Note that I commented out the display function on line 28, or 29 rather. So what I've done there is I've, in essence, directly interrogated memory where that class object is sitting, and we found out that the object is the private data. When you look at this class declaration here, you get the impression, well, there must be some sort of fancy, funky function stuff there at the beginning of the class object. No, the object's just the data. And in fact, I specifically put the public functions first to really drive it home that no, that there isn't some weird class stuff happening after those 3 long integers. That's it, the 3 long integers. Let's find out how large. How much memory does MC take? Cout size of MC equals size of MC and 1. 82463. Where did I come up with that? 81624. Where did I come up with 82463? I don't know. I have the slightest idea. Does that mean anything? I think that's like some weird global world order secret number thing there that I'm part of a conspiracy of, and I let it slip. You're all going to have to die. All right. Yes?
Would it print 1024 just basically where to put cout, we just put IP and out for that, and line for that, or would it just print?
If I print IP by itself?
Yeah, IP, well, obviously.
Oh, you want me to do this? So you're asking the equivalency of this line and this line? Yeah, I mean, it's intuitively and in actuality the exact same. You're adding nothing to that initial address and you're dereferencing it. Yeah.
So my question is, what about the function pointers? How we did with C-style way, we replaced the member function with the function pointers. Function pointers are pointers; they must take up some amount of memory.
So I haven't connected all the dots yet, because I was doing some funky fancy stuff with the C code there, or you all were, and they're clearly, and I even drew the diagram with function pointers in there. So let's start to get to the bottom of that mystery. And to get to that, first we have to talk about what is exactly happening with the code when we compile. Let me come back up to our, let me blow this up here. Let me come back to the constructor. What I'm going to do is I'm going to not use, we all know that, we all now know that this is considered poor form for me to initialize the data member of an object, data members of an object this way. But setting that aside, what if I change this variable name to first? What happens? Yeah.
I would suspect that because first was uninitialized, it got initialized with a garbage value, and then because it's in scope, it looks first equals first, and it assigns the garbage value to itself.
So what yeah, I think you're on the exact right track. You've got it backwards though. So your assertion is on line 17 that the object's first variable assigns to itself and it hasn't been initialized yet, so it's all garbage. Okay, it's the other way around. The declaration on line 14 hides the object's variable. So it is the 10, right? The 10 I pass in, and the 10 is copied into first. And so basically I'm taking that 10 and I'm reassigning it to itself.
10 is reassigned to itself, and the
the object data member called first is uninitialized. So how do I correct this line in order? Yes, exactly. That's exactly right. That's how you solve that problem, right? In fact, that's implicit in all the C++ code you write, is that if you don't put it in there, the compiler puts it in there for you. Even these here, these aren't necessary to compile for us, but that's actually what the compiler does. Right. Right, I mean that's the normal course of action, is that people make it, at least in this example, you make the input parameters have different names from the member data, but it isn't an issue for us as long as we add this pointer. But let me elaborate on that a little bit. Linker technology. So let's talk about linkers for a minute. We know that we go through the preprocessor, the compiler, the assembler, then the linker. All right, our assembler and our linker, 40 years, we got pretty much the same technology. The stuff you're doing now with compiling and linking, that was what was happening 40 years ago. Now there are additional bells and whistles and some stuff with shared libraries that are niceties, but the basic technology hasn't changed. And to quickly illustrate that, let me create some C code. And what do I want to do? Int, add them up. Now, this code's nonsensical, but that's all we need for purposes here. So we've got the function definition, and we're invoking the function. I can go ahead and I can compile that, and I'm going to use the -s option. Anyone recall what the -s option is to GCC or G++? Yes?
Generates assembly code file.
So it runs the compiler, and it suppresses the assembler, and it suppresses the linker. Right? So it stops with the assembly language code prior to going into the assembler. And if I do an ls, we see that there is indeed a .s suffix here. I can look at that. And we can see that largely the name's untouched. There's an underscore in front of it. But there's our call inside of main, and then here's the definition of our function up here. Okay. That is the same technology that has to be used with C++. There is no concept of class objects here at the assembler. There's simply functions that take parameters, the definition of those functions, and the calls to those functions. So there actually has to be a conversion that occurs when you have code like this. And what happens is that this, in this example, this constructor is converted to a normal C-style function. And the very first parameter is a pointer to the object. And what is the object? It's nothing but the data. So all of these fancy C++ functions we write just become ordinary C functions where the first parameter is the address to all the data comprising that object that you want to operate on. It's a little bit more complicated than that in that I can have more than one constructor, right? I can have a constructor that takes 0 and write a default constructor, for example, and we code it up to initialize first, second, and third to some predefined values. The reason I mention that is that by my formula that I've done on the line where my cursor is, I would have to create another function called myClass. Now we have naming collision. And we could have 20 display functions as long as what's returned in the input parameter, either number of input parameters or type of input parameters are different. You can have multiple display functions. Well, how does the C++ compiler get around that limitation? Yes?
Name mangling.
Name mangling. I like the gusto with which you said that. All right. Name mangling. Let's look at an example of that. Let me call this function add 'em up. This is, what did I take? An integer A and an integer B. I'm going to come down here. I'm going to say my class, colon, add 'em up. So it's the same function. I'm just making it a member function. And now I need to get my other cruft out of here so the thing compiles. I did comment it out. I think we're good. No, we're not good. Did I say return? Oh, and I said void. Int. All right. Compile. That compiles. Now let me go ahead and do it with the -s option so we can look at the assembly code. So here we see the phrase add 'em up, but now there's a bunch of other crap thrown on there. So here's the name of the class. This, I assume, means that it takes 2 integer parameters. Now I don't know, I haven't tried it. My guess is if I went in here and created a second add 'em up function, well, we may as well do it. Make these floats. Whoops. And then I will just copy 16 through 19, is that right? 16 through 19, yank, put, float, float, oops. Come over here, recompile, re-examine. Yeah, here you go. You see they changed them to F's for the 2 floats. So that's what name mangling is it's a way to convert from your member function definitions to the good old-fashioned C-style definitions, and at the same time ensuring every one of them is unique. Yes?
Where is the first parameter to this? in this assembly code, you have two floats, F, and what about the first? Is it the E? The first.
Yeah, I don't know. I don't know the exact algorithm they're using to do the name mangling, but presumably there's something like that. Every single I guess, I don't know. You could try creating a non-class function. Now you try different things. What if you try a static function? What does it generate, right? There's going to be some algorithm for generating this. It suffices for our interest that it generates a unique name. All right, so make sure I don't leave any stone unturned here. Now we need to get back to this, because this has function pointers and my example doesn't. And there's a key difference between, say, the media class and my class. What if, now let me actually run this code since I've been messing around with it a little bit, make sure that it's doing what we think. All right, so we get the 10, 20, 30, and we print out its size as 24, right? We're doing that here by interrogating memory directly for that object. Let me make one change. There you go. Let's try compiling it. Let's run it. So you all help me fill in the blanks now. Help me draw. I can't put everything on the screen. Help me draw one of these boxes. What's it going to look like? I'm going to have a, let's choose an appealing color. This black. So I draw my, yeah, we're just going to run with it, all right? You can, on the course reviews, you can have something for my drawing ability.
Seems like the first field is the function pointer. That's the number.
And then what's the second field?
The first, second,
I'll just do it like this.
third, and
Yeah? All right. So by putting the keyword virtual in there and dealing with virtual functions, that's when we get the function pointers. Now, what's been drawn in blue here is not quite how it works, because that would be two virtual functions, if you will. And in fact, if you have 2, 5, 10 virtual functions, you don't have 2, 5, 10 pointers in there. What you have is just a single pointer. So this whole thing in reality is compressed to a single pointer, and that single pointer takes you to what's called basically a table of virtual function pointers. So this then would be area pointer, and this one would be, what do we have, draw. And I'm really small, and I shouldn't have done it that small. Right, so this would just be a single pointer going to this virtual table, virtual function pointer table. Huh?
to the VT0.
There you go. So this pointer that we're seeing here, where is it? Right here. This address is not the address of, what did I make? Display I made virtual. This is not the address of the display function. This is the address of the table, and in that table there's exactly one entry for that display function. That's because I printed it out as a long integer. If I print ampersand MC, I'll get the hex. Yeah, I'll get the hex equivalent to that number. So the final piece of the puzzle then is the word virtual itself. why do we have to put the word virtual in? Java has polymorphism. Python has polymorphism. We don't have to put virtual or something like that. You just do it and it works, right? Here, if you don't put the word virtual, the thing breaks horrendously. Why is it that C++ is the weird one where they make us, the language designers have made us put the word virtual in there? Yeah?
I would suspect that perhaps because C++ was designed to be backwards compatible with C, they couldn't abstract some of the more some of the details away from the user, perhaps.
Okay, yeah. So I think as a generalization for backward compatibility with C, but let's get more into the philosophy of it. So I'd mentioned that I'm going to be teaching systems programming next semester. And one of the things we do in systems programming is we create a chunk of shared memory that multiple processes utilize. And to create a chunk of shared memory, you use malloc, which is the C-style system call for allocating memory. In fact, if you were to dig down into the source code of the new operator, you'd find in there's a call to malloc. That is the way of allocating memory in a Unix-based system. Okay? And the argument to it is a number of bytes. So you say malloc and I want 300 bytes. Well then, whenever you want to access that memory, it's just raw bytes. What you have to do is you have to overlay something with meaning on top of it. So what you do is you take a C-style structure, which is just the data, and you overlay that through casting, right? You use casting to say that memory is not raw bytes. That memory is my, I don't know, your widget structure. And now you just interact with this widget structure, and it's going to map into various offsets in that memory, right? In the same way that we had various offsets here, various offsets for those three long integers.
The dot operator.
Yeah, the dot operator, or if you're in that level, you're dealing with pointers, so you'd be using the arrow instead of the dot.
So yeah, just
So C is a language where you as the programmer have an intimate knowledge of how your information, basically, I don't even want to call it information, I want to call it data, how your data is laid onto the system's memory. You can look at any data structure, it's got three longs and a float and an int and a short and a character. The character's probably going to buffer out to the size of a word, right? But if you know these things as a programmer, you know how to map all that memory out. And you need to be able to do that kind of thing when you're programming at a systems level because you are dealing with low-level memory. Well, the minute you throw in, so that, because it's true in C, it's also true in C++. But the moment you take advantage of these nice features of object-oriented programming, specifically the polymorphism, you have to have that additional pointer in your data. Now, it isn't data anymore. It's not data where you know where it is. It's information. It's a triangle object or a circle object or a book. And you don't know how that lays out in memory because somewhere in there is a pointer. So they're saying, if you want to get away from the machine and no longer know where your data is and just consider it information, that's fine. Don't make us do it. You do it. You put the word virtual there. So they're leaving you as the programmer control over that. What about inheritance? Looking at these pictures here, tell me if I was to create a book object. Oh, actually, let me take a step back and say one other thing. Regarding this pointer, we saw that it was the very first element, and here it was the second element, second and third, but if we go with it, run with this idea, it'd be the second element. That is implementation dependent on where it is. Where would it be incorrect to put it? Where would it break things to put that pointer? Yeah?
at the very end.
Yeah, at the end, because you don't know how many things are in that chunk of data, right? So you'd have no way to get a consistent offset. So it has to be in a known location. As long as it's in a known location, then you're good. I put it in the second actually just based on how I cut my teeth. On the C++ compiler, early compiler I used, it actually did put that pointer as the second element. Also, when I was first using C++, they did not have a compiler that compiled down to assembly. They had a compiler that compiled down to C code, and you compiled the C code then. And when you, so what you would do is you'd run it through the C++ compiler, you'd have a bunch of C code, you examine it, that's where you learn about what the this pointer is doing and the pointer for virtual functions and so on and so forth, right? Because it was all there in C code to see. And now it was generated, so I'm not saying it was a walk in the park, but it's something you could get around with a bunch of people and kind of noodle through. Yeah.
Is there an option in G++ to have it on C?
I don't know. Is there? Anyone know for a fact?
I don't know. What was the name of the compiler?
Cfront was the name of the C++ compiler I was using, Cfront. Anyway, so that isn't important. So the shit, there's one last thing I wanted to say, and now I don't remember it. Any questions? Oh, yeah. I was talking about the book. That's where I got off track. So if I was to draw a box and draw a book object, I say book BK. How would I make it look? This time I'm going to abandon my drawing skills. And we know that it has a virtual function, and we know we're using G++, so it's going to have the pointer in the same place it did here. So we know that we're going to have a function pointer here that's going to get to our virtual jump table that has the display function, the destructor, whatever we made virtual in that application. What follows? What's going to be the next piece of data in there? Yeah. What's going to be the first attribute of that book? How many of them are there going to be, not counting this function pointer? Okay, that's what I wanted to get at. You said 6. No, there are 10. If you create a book object, there are 10 pieces of data. Look at this. Look at these two. Can you imagine? It's easy to imagine this in C++ where you've abstracted out a shape type, and what attributes are in shape? Color and shade. Yeah? So inheritance is nice for us as programmers, but in actuality, when it's implemented in the code, a book has 10 attributes, a periodical has 12 attributes, and so on and so forth. And the initial attributes, the first attributes, are the base class. And that actually makes complete sense because you have member functions that are in the base class, right? And they're not virtual. Those member functions in the base class that aren't virtual, at compile time, it's determined what the behavior is. And that makes sense because at compile time, what's an example? It's compare title, right? That's determined that it's not virtual. Well, compare title, it's going to say go to this offset to grab the title and do some sort of comparison. Well, that offset's consistent. It never changes, regardless of whether it's a book, a film, a video, or whatever, because all that information appears first in the exact same order, regardless of type. That makes sense? All right. So that's what I wanted you to see with all the in-class stuff to lead up to this idea. What I want to do next is we now have another project. I think it's the exception handling project. And if you all before class on Monday could just read through the materials, I can't imagine it'd take you more than like 10 minutes or so. In fact, what's that? I'm sorry, say it again.
Which one takes 10 minutes, the reading or the project?
Oh, I'm sorry, I misinterpreted what you said. the reading, right? The project will take a bit longer. Although I will say, with the exception of the string substitution project, a lot of these projects have a tremendous amount of head scratching where we pick at the unknowns in class, and once you understand it, the actual code, there's very little code in a lot of these projects. That includes this one here. So the actual code, you aren't going to have to spend a tremendous amount of time creating hundreds and hundreds of lines. Some of them are dozens, a couple dozen.
I think we have an assignment due this Sunday.
Oh, okay. Yeah, so that's what I wanted to look at. So maybe I will have an assignment for you. It's a real easy assignment. So before you leave, I know that I'm out of time, but if you'll bear with me for just 30 seconds. Yes, I can't do anything until you all do a little bit of work. So I need you to do this first deliverable. And what it is the mechanics of exception handling are pretty straightforward if you haven't ever used it. Try, throw, catch. You have 3 keywords. I just need you to go look at a tutorial, get a mechanical understanding, and then the first assignment, it emphasizes 1 page or less, don't go to town, create a cheat sheet on how you use the exception handling facilities in C++. Show a little example code. I mean, you could in principle, I wouldn't want you to, but you could in principle literally copy and plagiarize something. I'm not going to go out and it's a waste of my time to see if you've done that. I just need you to understand the mechanics so I don't have to do a lecture on that. And then we'll get into the project on Monday. Okay?
That's due Sunday?
Yeah.
Okay.
All right.